There is a world that turns in the darkness, just as our own world turns. It moves through the void at a pace both familiar and strange, spinning on an axis tilted at 25.19 degrees, so close to Earth's own tilt that the similarity feels almost intentional, though it is simply the way things settled billions of years ago. This world is Mars, the fourth planet from our Sun, and it exists in a state of quiet persistence, rotating and revolving through the same cosmic rhythms it has followed for longer than any human memory, longer than any civilization, longer than our species has walked upright. Mars completes one full rotation in 24 hours, 39 minutes, and 35.244 seconds. This duration, called a sol by those who study the planet, differs from an Earth day by less than 3%. If you were standing on the Martian surface, watching the stars wheel overhead, you would find the passage of time to be almost recognizable. The sun would rise in the east, just as it does here. It would arc across a sky of butterscotch and rose, colors born from fine dust suspended in an atmosphere 100 times thinner than our own. Then it would set in the west, and the stars would emerge, and the night would pass in stillness before the cycle began again. This similarity in day length is one of the quiet coincidences that connect our two worlds. Mars and Earth share more than just their rotation rates. Both planets have seasons, created by the tilt of their axes. Both have ice caps at their poles that grow and shrink with the changing year. Both have weather, though the weather on Mars is slower, gentler in its forces, constrained by an atmosphere too thin to hold much energy. These parallels exist without purpose, without meaning, beyond the simple fact that they emerged from similar physical laws acting on similar materials in slightly different conditions. The distance from Mars to the Sun averages about 230 million kilometers, though this distance changes as the planet follows its elliptical path through space. At perihelion, its closest approach, Mars draws near to 207 million kilometers from our star. At aphelion, the most distant point in its orbit, that distance stretches to 249 million kilometers. This variation of more than 20% affects how much sunlight reaches the Martian surface, creating a difference of 45% in solar intensity between the warmest and coldest parts of its year. It takes Mars 687 Earth days to complete one orbit around the Sun. In Martian sols, this same period encompasses 668.59 sols. The longer year means that Mars experiences seasons almost twice as long as those we know on Earth. But because of the planet's eccentric orbit, these seasons do not divide evenly. In the northern hemisphere of Mars, spring lasts 194 sols, making it the longest season. Summer follows with 178 sols. Then comes autumn, the shortest season at 142 sols, and winter spans 154 sols. The seasons in the southern hemisphere reverse this pattern, with the longest season occurring when the northern hemisphere experiences autumn. The eccentricity of the orbit creates another effect, one that shapes the climate of each hemisphere differently. When Mars reaches perihelion, receiving the most intense sunlight, the planet's southern hemisphere tilts toward the Sun, bringing summer to the south. 6 Martian months later, at aphelion, the northern hemisphere enjoys its summer while receiving significantly less solar energy. This coincidence of geometry means that southern summers on Mars are hotter and shorter than northern summers, while southern winters stretch longer and colder than their northern counterparts. The difference can reach 30 degrees Celsius in temperature, a substantial variation that drives much of the planet's atmospheric behavior. Mars rotates in the same direction as its orbital motion, spinning counterclockwise when viewed from above its north pole, just as Earth does. This prograde rotation means that the solar day lasts slightly longer than the sidereal day, the time it takes for the planet to rotate once relative to the distant stars. That sidereal period measures 24 hours, 37 minutes, and 22.663 seconds. The additional 2 minutes and 12 seconds in the solar day account for the small amount that Mars moves along its orbit during each rotation. There is something settling about these measurements, these careful accountings of time and distance. They represent the outcome of observations made over centuries, refined through countless nights of patient watching as Mars moved against the background stars. Early astronomers noticed that Mars did not follow a simple path, through the sky. Instead, it occasionally appeared to move backwards, tracing loops against the constellations. This retrograde motion puzzled observers for generations until they understood that it resulted from Earth overtaking Mars in its inner, faster orbit, creating an optical illusion of backward motion. The understanding of Mars's true orbit came gradually, built observation by observation. In the early 1600s, Johannes Kepler studied the precise measurements that Tycho Brahe had made of Mars's position over many years. Kepler discovered that Mars's orbit could not be a circle, as had been assumed for centuries. Instead, it traced an ellipse, with the Sun at one focus of that ellipse. This realization became the first of Kepler's 3 laws of planetary motion, fundamentally changing how we understood the cosmos. Mars, through the peculiarity of its eccentric orbit, helped reveal one of the basic patterns that governs how planets move. The planet turns now just as it turned then, indifferent to observation, following the same elliptical path through space. There is no variation in this pattern, no uncertainty. The gravity of the Sun holds Mars in its orbit with the same steady force it has exerted for billions of years. The planet's rotation continues at the same rate it maintained when Earth was still molten, when the first oceans condensed, when life first emerged in those ancient waters. Mars was already old when Earth was young, and it will continue turning long after all human endeavor has ended. What follows is an exploration of this distant world, not as a destination for conquest or colonization, but simply as a place that exists. We will move through the characteristics of Mars slowly, examining each feature without hurry. There is no dramatic revelation waiting at the end of this journey, no stunning conclusion. There is only Mars itself, turning in the darkness, carrying its burden of rust-colored dust, its ancient volcanoes, its frozen caps of water ice and carbon dioxide. This exploration will not demand your full attention. You can let the details wash over you like distant music, taking in what interests you and releasing what does not. The facts presented here come from decades of careful observation, from spacecraft that have orbited the planet and rovers that have touched its surface, from instruments that have measured its atmosphere and mapped its terrain. Every number, every distance, every temperature has been verified through multiple methods, cross-checked against different sources of data. Where uncertainty exists, it will be noted. Where theories remain unconfirmed, that tentativeness will be acknowledged. We will begin with the atmosphere of Mars, that thin envelope of gas that separates the surface from space. Then we will explore the ice caps, vast deposits of frozen water and carbon dioxide that grow and shrink with the seasons. We will examine Olympus Mons, the largest volcano in the solar system, a mountain so vast that you could not see its peak from its base due to the curvature of the planet. We will trace the length of Valles Marineris, a canyon system that stretches across nearly a quarter of the planet's circumference. We will consider the dust storms that occasionally engulf the entire world, turning the sky opaque for months at a time. We will meet the two small moons that orbit Mars, irregular chunks of rock that circle the planet on timescales measured in hours rather than weeks. Each of these features exists in its own right, shaped by forces that operated over geological timescales. The atmosphere thinned gradually as solar wind stripped lighter gases away over billions of years. The ice caps accumulated through countless cycles of freezing and sublimation. Olympus Mons grew through episode after episode of volcanic eruption, building itself higher as lava cooled and solidified. Valles Marineris opened as the crust fractured and collapsed. The dust storms arise from the interaction between solar heating, atmospheric circulation, and the fine particles that cover the surface. The moons, Phobos and Deimos, settled into their current orbits through processes that remain not entirely understood, possibly captured from the asteroid belt, possibly formed from debris ejected by an ancient impact. There is no need to hurry through these topics. Mars has existed for 4.5 billion years. It will continue to exist for billions more. The information contained here represents what we currently know, but that knowledge is incomplete and will remain so. We have visited Mars with machines, but not with people. We have sampled its rocks and soil at a handful of locations, but not everywhere. We have photographed its surface in extraordinary detail, but cannot see beneath that surface except in limited ways. What we know is accurate within the bounds of our measurements. What we do not know vastly exceeds what we do. You might choose to rest while listening to these facts. You might close your eyes and let the words create images in your mind, pictures of a red world turning beneath an alien sun. You might drift in and out of full awareness, catching fragments of information that settle into memory while others pass by unnoticed. This is not a test. There will be no questions afterward. The value in this knowledge lies not in retaining every detail, but in allowing yourself to contemplate a world beyond our own, to recognize that the universe contains places both similar to and different from Earth, and that these places continue their existence whether we think of them or not. The pace of what follows will remain steady and slow. Transitions between topics will occur gently, without abrupt shifts. The tone will stay calm throughout. There is drama enough in the bare facts themselves, in the enormous scale of Martian features, in the extremes of temperature and the violence of global dust storms, without adding artificial emphasis. The numbers speak for themselves. The distances require no embellishment. The timeframes involved dwarf human experience so completely that any attempt to make them more impressive would be futile. So let us begin with the atmosphere, that thin shell of gas that clings to Mars through gravity, too weak to hold liquid water on the surface, but thick enough to generate weather, to carry dust, to create clouds and frost and even snow. The atmosphere of Mars is where much of the planet's active behavior takes place, where the most visible changes occur from season to season and year to year. Understanding the atmosphere provides a foundation for understanding everything else about the planet, because nearly every process on Mars interacts with its atmosphere in some way. Carbon dioxide makes up 95.32% of the Martian atmosphere by volume. This is the gas that we exhale, the gas that plants absorb, the gas that dissolves in seawater and forms carbonates in limestone. On Mars, there are no plants to absorb it, no oceans to dissolve it, no biological processes to cycle it through living systems. The carbon dioxide simply exists in the atmosphere, the dominant component by far, more abundant than all other gases combined. The remaining 4.68% of the atmosphere consists primarily of nitrogen at 2.7%, argon at 1.6%, and oxygen at 0.13%. Water vapor exists in trace amounts, varying with location and season, but never exceeding a few molecules per 10,000. Carbon monoxide, produced by the breakdown of carbon dioxide molecules in the upper atmosphere, accounts for another tiny fraction. Noble gases like neon, krypton, and xenon exist in quantities measurable only with sensitive instruments. The atmosphere that contains these gases is extraordinarily thin. At the surface of Mars, the average atmospheric pressure measures approximately 600 pascals, though this value varies with both location and season. To put this in perspective, Earth's atmospheric pressure at sea level is about 101,300 pascals. The Martian atmosphere exerts less than 1% of the pressure that Earth's atmosphere creates. This low pressure has profound consequences for everything on the planet. Water cannot exist in liquid form at such low pressure. The triple point of water, the unique combination of temperature and pressure where ice, liquid, and vapor can coexist in equilibrium, occurs at 610.5 pascals and 0.01 degrees Celsius. The pressure on Mars averages just slightly below this value, and the temperature is almost always well below freezing. This means that any ice on the Martian surface cannot melt. It can only sublime, transforming directly from solid to vapor without passing through the liquid phase. Likewise, any liquid water exposed to the Martian atmosphere would immediately begin to boil, even at temperatures far below freezing, as the low pressure pulled water molecules into the vapor state. The low density of the atmosphere also means that sound travels differently on Mars than on Earth. Measurements from NASA's Perseverance rover have confirmed that the speed of sound on Mars is approximately 240 meters per second for frequencies below 240 Hz and 250 meters per second for frequencies above that threshold. This is notably slower than the 343 meters per second that sound travels through Earth's atmosphere at sea level. The difference arises from the atmosphere's composition and pressure. Carbon dioxide molecules are heavier than the nitrogen and oxygen molecules that dominate Earth's atmosphere, and the lower density of the Martian atmosphere further reduces the speed at which pressure waves can propagate. This thin atmosphere cannot hold much heat. During the day, when sunlight strikes the surface, the ground warms considerably. But at night, with no thick blanket of air to retain that warmth, the heat radiates rapidly back into space. The diurnal temperature range on Mars, the difference between daytime and nighttime temperatures, can reach 50 degrees Celsius or more at some locations. On Earth, even in deserts where the air is dry and the sky is clear, the temperature swing rarely exceeds 20 to 30 degrees. Mars experiences these extreme swings every single day, a consequence of the weak greenhouse effect produced by its thin carbon dioxide atmosphere. The atmospheric pressure varies significantly with elevation on Mars. This might seem obvious since pressure decreases with altitude on any planet, but the effect is more pronounced on Mars due to the thinness of the atmosphere and the extreme topographic relief. Olympus Mons, the tallest volcano on the planet, rises 21.9 kilometers above the surrounding plains. At its summit, the atmospheric pressure measures only 72 pascals, about 12% of the already low average surface pressure. This is roughly equivalent to the atmospheric pressure at 35 kilometers altitude on Earth, far above where any aircraft can fly. Conversely, in the deepest depressions on Mars, the pressure rises above the average. Hellas Planitia, a massive impact basin in the southern hemisphere, drops more than 7 kilometers below the reference level used for Martian elevations. At the bottom of Hellas, the atmospheric pressure can reach 1,155 pascals, nearly twice the planetary average. This is still less than 1% of Earth's sea level pressure, but it represents a substantial variation within the Martian environment. The atmosphere also varies with season in a way unique among the planets. Because carbon dioxide makes up such a large fraction of the Martian atmosphere, and because temperatures at the poles fall low enough for carbon dioxide to freeze, a significant portion of the atmosphere itself condenses and deposits onto the polar ice caps during winter. As much as 25 to 30% of the total atmospheric mass can freeze out at one pole or the other during the depths of winter. This mass transfer is large enough to cause measurable changes in the planet's gravity field, detected by orbiting spacecraft as the distribution of mass shifts between the poles and the atmosphere. When winter comes to the northern hemisphere, temperatures at the North Pole drop to around negative 153 degrees Celsius. At these temperatures, carbon dioxide gas in the atmosphere condenses directly into frost and snow, falling onto the existing polar cap. A seasonal layer of dry ice accumulates, about 1 meter thick, covering the permanent water ice cap beneath. The atmosphere grows thinner as this mass is removed from the gas phase. Pressure drops. Globally, not just at the pole where the freezing occurs, every part of Mars experiences this seasonal thinning of the air. Then, spring arrives. As the North Pole tilts toward the Sun and temperatures climb above negative 130 degrees Celsius, the seasonal dry ice begins to sublime. Carbon dioxide transitions directly from solid to gas, returning to the atmosphere. The global pressure rises again as this mass is restored to the air. Meanwhile, winter is arriving at the South Pole, where the same process begins in reverse. The South Polar seasonal cap is thicker than the northern one, accumulating about 8 meters of dry ice rather than just 1 meter. This asymmetry arises from the interaction between the Martian seasons and the planet's eccentric orbit. The South Pole experiences winter when Mars is near aphelion, its furthest point from the Sun. This means southern winter is longer and colder than northern winter. More time and more cold allow more carbon dioxide to freeze out of the atmosphere. The South Polar seasonal cap grows larger and thicker as a result. This creates a variation in atmospheric pressure that follows the Martian year, with the lowest pressures occurring during southern winter and the highest during southern summer. The pressure variation is not trivial. It amounts to roughly 8% of the mean pressure, a noticeable change that affects weather patterns across the entire planet. Water vapor in the Martian atmosphere behaves similarly to carbon dioxide, though in much smaller quantities. The atmosphere of Mars is effectively saturated with water vapor, meaning that it contains about as much water as it can hold at its current temperature and pressure. But because both temperature and pressure are very low, the absolute amount of water vapor is tiny. If all the water vapor in the Martian atmosphere were to condense at once and fall uniformly across the planet, it would form a layer only about 10 to 20 micrometers thick, roughly the diameter of a human hair. Despite this scarcity, water plays important roles in Martian atmospheric processes. Water ice clouds form in the atmosphere, particularly around the poles during autumn and winter. These clouds can be quite extensive, sometimes developing into polar hoods that cover large portions of the high-latitude regions. The clouds consist of ice crystals that scatter sunlight, giving them a white or bluish appearance in images taken from orbit. Near the surface, water ice frost appears on rocks and soil during cold nights, subliming away as the sun rises and temperatures increase. This daily cycle of frost formation and sublimation occurs in many regions, particularly at higher latitudes. The atmosphere also contains dust, an ever-present component that gives the Martian sky its distinctive colors. The dust particles are extremely fine, averaging about 1.5 micrometers in diameter. They consist primarily of iron-rich minerals that have oxidized, creating the rust-like compounds that give Mars its red appearance. These particles remain suspended in the atmosphere for long periods because the thin air provides little resistance to keep them aloft, while the weak gravity exerts less pull than it would on Earth. Once lifted into the atmosphere, dust can stay airborne for weeks or months, gradually settling out over time, only to be lifted again by the next dust storm. The presence of atmospheric dust affects the appearance of the Martian sky. When dust content is low, the sky appears butterscotch or pinkish tan, with subtle variations in shade depending on the angle of the sun. During dust storms, when dust loading increases dramatically, the sky can turn nearly opaque, blocking out the sun and creating a murky, reddish-brown pall. Even in the clearest conditions, the Martian sky never appears the deep blue that we see on Earth. The thinness of the atmosphere and the scattering properties of the suspended dust particles prevent that particular color from emerging. Scientists measure atmospheric dust loading using a parameter called tau, which indicates optical depth. A tau value of 0 would mean perfectly clear air with no dust. A tau of 1 means that the atmosphere is opaque enough to block about 63% of direct sunlight. During normal conditions on Mars, tau typically ranges from about 0.1 to 0.5. During moderate dust storms, it might reach 1 or 2. During the largest global dust storms, tau can exceed 5 or even 10, reducing sunlight at the surface to a few percent of normal levels. The atmosphere of Mars has changed substantially over the planet's history. Evidence from isotopic measurements suggests that Mars once possessed a much thicker atmosphere. The ratio of different isotopes of elements like nitrogen and argon indicates that lighter isotopes have been preferentially lost to space, a signature of atmospheric escape. Nitrogen-14, the lighter isotope, has been stripped away more readily than nitrogen-15, leaving the remaining nitrogen enriched in the heavier isotope by about 75% compared to Earth. This enrichment implies that Mars has lost a significant fraction of its original nitrogen inventory. Similar patterns appear in measurements of other atmospheric gases. The deuterium to hydrogen ratio in Martian water vapor is about 5 times higher than in Earth's oceans, indicating that lighter hydrogen has escaped while heavier deuterium remained. The loss of hydrogen directly correlates with the loss of water, since water molecules that are broken apart in the upper atmosphere can lose their hydrogen to space. The current atmosphere of Mars is a remnant, what remains after billions of years of gradual stripping by solar wind and ultraviolet radiation. The planet lacks a global magnetic field, a consequence of its small size and the cooling of its interior. Earth's magnetic field deflects much of the solar wind, the stream of charged particles flowing outward from the sun. Mars has no such protection. The solar wind interacts directly with the upper atmosphere, transferring energy and momentum to atmospheric particles. Over geological time, this interaction has peeled away much of the atmosphere that Mars once had. Measurements from NASA's MAVEN spacecraft, which orbits Mars specifically to study atmospheric escape, have quantified the ongoing loss. Mars continues to lose atmosphere to space today, though at rates far slower than the loss that occurred in the planet's early history when the sun was more active and solar wind was more intense. The thin atmosphere that remains is enough to generate weather, though Martian weather differs in character from the weather we experience on Earth. Temperature differences between the equator and the poles and between day and night drive atmospheric circulation. Warm air rises, cold air sinks, and these vertical motions create horizontal winds that transport air masses across the planet. At low latitudes, Hadley circulation dominates, with air rising near the equator, flowing toward the poles at high altitude, then sinking at mid-latitudes and returning toward the equator near the surface. This is the same circulation pattern that creates Earth's trade winds. At higher latitudes on Mars, baroclinic waves form, regions of alternating high and low pressure that sweep around the planet from west to east. These waves result from the temperature difference between the cold polar regions and the warmer mid-latitudes. They can spawn weather fronts, areas where air masses with different temperatures meet and interact. While Martian frontal systems are less dramatic than those on Earth due to the thin atmosphere and low energy available, they can still produce significant wind and dust transport. The atmosphere of Mars provides enough substance for weather to occur, enough mass for pressure gradients to form, and winds to blow, but not enough to make the planet hospitable. It is an atmosphere in decline, a remnant of something larger, continuing to thin as solar wind strips it away molecule by molecule. Yet within this thinness, within these few hundred pascals of pressure, complex processes continue. Clouds form and dissipate. Frost accumulates and sublimes. Dust rises and falls. The atmosphere remains active, responsive to solar heating and seasonal changes, creating a dynamic environment despite its fragility. At both poles of Mars, ice accumulates in quantities large enough to shape the landscape and influence the global climate. These polar ice caps are permanent features, though they grow and shrink with the seasons. They consist primarily of water ice layered with dust, covered during winter by seasonal caps of carbon dioxide ice. The two caps differ in detail, shaped by their different elevations and the asymmetric seasons created by Mars's eccentric orbit, but both follow similar patterns of accumulation and sublimation. The North Polar Cap sits at a relatively low elevation, with its base around 5,000 meters below the reference level and its summit around 2,000 meters below that level. It spans approximately 1,000 kilometers in diameter during northern summer, when the seasonal carbon dioxide has completely sublimed away. The cap contains about 1.6 million cubic kilometers of water ice, enough to cover the entire planet to a depth of about 10 meters if it was spread uniformly across the surface. This represents a substantial reservoir of frozen water, though it is only a fraction of the ice that exists elsewhere on Mars in the form of underground permafrost. The water ice in the North Polar Cap is not pure. It contains layers of dust interspersed with the ice, creating visible layering when viewed from orbit or from the side where erosion has carved into the cap. These layers record the climatic history of Mars, deposited during periods when the planet's obliquity, the tilt of its axis, varied from its current value. Mars's obliquity changes substantially over timescales of tens of thousands to millions of years, varying between about 15 and 35 degrees. When obliquity is high, the poles receive more direct sunlight during summer, leading to different patterns of ice accumulation and sublimation. The layers in the polar caps preserve this history, though reading the record remains challenging. During northern winter, the seasonal cap of carbon dioxide ice begins to form as temperatures drop below the frost point of carbon dioxide. The cap expands dramatically, eventually extending down to about 60 degrees north latitude, covering an enormous area. This seasonal cap consists of a thin layer of dry ice, about 1 meter thick at its maximum extent. Clouds of water ice and carbon dioxide ice crystals form over the cap, creating what is called the polar hood. Precipitation falls from these clouds, thickening the seasonal cap. This deposition process continues throughout the winter, reaching its peak extent in late winter. As spring arrives and temperatures rise, the seasonal dry ice cap begins to sublime. The process starts at the edges where the ice is thinnest and works inward toward the pole. By the end of summer, all the seasonal carbon dioxide has returned to the atmosphere, exposing the underlying permanent cap of water ice. The water ice does not sublime completely because summer temperatures at the North Pole, while rising above the frost point of carbon dioxide, remain well below the frost point of water ice. The permanent water ice cap persists year-round, accumulating very gradually over thousands of years. The South Polar Cap differs in several important ways. It sits at a much higher elevation than the North Cap, with its base around 1,000 meters above the reference level and its summit reaching about 3,500 meters above that level. This higher elevation means that atmospheric pressure at the South Pole is lower than at the North Pole, affecting sublimation rates and the behavior of both water and carbon dioxide ice. The cap's diameter during summer is smaller, only about 350 kilometers, but its thickness reaches about 3 kilometers, similar to the North Cap. Perhaps the most striking difference is that the South Polar Cap retains a layer of carbon dioxide ice year-round. While the North Polar seasonal cap completely sublimes during summer, the South Polar Cap keeps a permanent residual layer of dry ice about 8 meters thick. This persists because southern summer coincides with aphelion, when Mars receives the least solar energy. The reduced solar heating is insufficient to sublime all the carbon dioxide that accumulated during the longer, colder southern winter. This permanent dry ice cap sits on top of water ice, creating a layered structure of different ices. The residual dry ice cap in the south has unusual features visible in orbital imagery. It appears pitted, with circular depressions that give it a texture sometimes described as resembling Swiss cheese. These pits form through a process of differential sublimation. Areas that are slightly darker than their surroundings absorb more sunlight and sublime more rapidly, creating depressions. Over time, these depressions deepen and widen as sublimation continues preferentially in the darker areas. The floors of the pits likely expose water ice beneath the carbon dioxide layer, which is less reflective than dry ice and thus absorbs more heat. During southern winter, the seasonal carbon dioxide cap expands even more extensively than its northern counterpart, reaching down to about 50 degrees south latitude. The cap grows thicker as well, accumulating 1.5 to 2 meters of dry ice from precipitation. The longer duration of southern winter, combined with the lower temperatures that occur when Mars is far from the Sun, allows this greater accumulation. As southern spring progresses into summer, this seasonal cap sublimes, but unlike in the north, a core of carbon dioxide ice remains year-round at the South Pole. The seasonal freezing and sublimation of carbon dioxide at the poles drives much of Mars's atmospheric behavior. When winter arrives at a pole and carbon dioxide begins to freeze out, the atmospheric pressure drops globally. Air flows toward the pole to replace the mass being removed from the atmosphere, creating strong winds. These winds can reach speeds sufficient to lift dust from the surface, sometimes triggering dust storms. In spring, when the frozen carbon dioxide sublimes and returns to the atmosphere, pressure rises again and winds blow in the opposite direction, away from the pole. This seasonal cycling creates a kind of atmospheric breathing, the the planet inhaling and exhaling as the poles alternately freeze and release their burden of carbons dioxide. Beneath the seasonal caps and beneath the permanent water ice caps, the subsurface of Mars contains enormous quantities of water ice in the form of permafrost. Ground ice exists at latitudes as low as 40 degrees in both hemispheres, extending down from just below the surface to depths of at least several meters. The Mars Odyssey spacecraft detected this buried ice using instruments that measure neutron emissions from the Martian surface, a technique that can identify hydrogen-rich materials like water ice. The Phoenix lander confirmed the presence of this ice when it landed at 68 degrees north latitude and dug trenches that exposed bright ice beneath a thin layer of soil. The volume of ice stored in the polar regions and in subsurface permafrost exceeds the volume visible in the polar caps by a substantial margin. Estimates suggest that if all the water ice on Mars were melted and distributed evenly across the surface, it would create a global ocean tens of meters deep. Most of this ice is locked in the subsurface, stable because temperatures at depth remain cold enough to prevent sublimation. Only at low latitudes, where temperatures are warmer, does ice become unstable in the near-surface environment. The polar regions also display other types of ice-related features. Gullies appear on some slopes facing the poles, narrow channels that show evidence of fluid flow carving into the terrain. The origin of these gullies remains debated. Some researchers suggest they formed through the melting of ice or the flow of briny water that remains liquid at temperatures below the freezing point of pure water. Others propose that they result from flows of dry granular material similar to avalanches. Recent observations have shown that some gullies are still forming today, with changes visible between images taken years apart. Frost forms and sublimes on a daily basis in many regions of Mars, not just at the poles. During cold nights, water vapor in the atmosphere condenses as frost on rocks, soil, and any other surface cold enough. As the sun rises and temperatures increase, this frost sublimes back into the atmosphere. The process is visible in images from landers and rovers, which have captured sequences showing frost appearing at night and vanishing by mid-morning. Carbon dioxide frost can also form during the coldest parts of winter at mid-latitudes, creating bright patches that persist for weeks before subliming when temperatures rise. The polar caps represent one of the most dynamic regions on Mars, changing dramatically with the seasons and hosting processes that occur nowhere else on the planet with such intensity. The seasonal growth and recession of the caps affects the global atmosphere, drives large-scale winds, and creates opportunities for dust storms to develop. The permanent caps preserve a record of past climates in their layered structure. The ice they contain represents the largest readily accessible reservoir of water on the planet, a resource that any future human presence would likely depend upon. Yet, despite this dynamism, there is something profoundly still about the polar regions. The processes that occur there happen slowly, measured in seasonal cycles that repeat with the regularity of orbital mechanics. The accumulation of ice proceeds at rates measured in millimeters per year. The erosion that carves features into the caps operates over timescales of thousands to millions of years. The overall pattern remains stable, oscillating within defined bounds, creating an environment that changes constantly yet remains fundamentally the same year after year, century after century. The ice caps will continue their cycles as long as Mars retains enough atmosphere to support the condensation and sublimation of carbon dioxide. They will grow each winter and shrink each summer, inhaling and exhaling mass, pulling the atmosphere down onto their surfaces and releasing it back into the air. This breathing will continue for as long as the planet exists in something resembling its current state, a rhythm as fundamental to Mars as the tides are to Earth, driven not by the pull of a moon, but by the changing angle of sunlight across the seasons. Olympus Mons rises from the surface of Mars to a height of 21.9 kilometers above the surrounding plains. This measurement, verified through laser altimetry data from orbiting spacecraft, makes it nearly 2.5 times taller than Mount Everest when measured from sea level on Earth. The volcano is so massive that its base spans approximately 600 kilometers in diameter, an area roughly equivalent to the entire country of France. If you stood at the center of Olympus Mons and looked toward its edge, the horizon would fall away before you could see the edge of the mountain. The slope would be visible, rising gently upward, but the full scale of the structure would remain incomprehensible from any ground-level vantage point. The slopes of Olympus Mons are remarkably gentle for such a tall mountain. The average gradient is only about 5 degrees, meaning that the elevation increases by only about 87 meters for every kilometer of horizontal distance traveled. This shallow angle results from the way the volcano formed, through countless eruptions of fluid basaltic lava that flowed long distances before cooling and solidifying. Each eruption added a thin layer to the growing mountain, and over millions of years, these layers accumulated to build the enormous structure that exists today. Shield volcanoes, the category to which Olympus Mons belongs, form through this process of gradual accumulation. They differ fundamentally from stratovolcanoes like Mount Fuji or Mount St. Helens, which are built from alternating layers of lava and ash from explosive eruptions. Shield volcanoes result from effusive eruptions, where lava flows relatively quietly from vents and spreads across the surface. The lava on Mars was likely similar in composition to the basaltic lavas that erupt in places like Hawaii on Earth, low in silica content and high in iron and magnesium, allowing it to flow easily before solidifying. The low viscosity of the lava explains why Olympus Mons grew so wide rather than tall and steep. Each flow could travel tens or even hundreds of kilometers from the vent before cooling enough to stop. These flows layered upon each other, building the mountain outward as much as upward. The result is a structure with enormous volume but relatively gentle slopes, a mountain you could theoretically climb on foot without technical equipment, though the journey would cover hundreds of kilometers and ascend more than 21 kilometers in elevation. At the summit of Olympus, Mons sits a complex caldera, a collapsed depression that formed when magma chambers beneath the volcano emptied during eruptions and the overlying rock fell into the void. The caldera measures approximately 80 kilometers across and contains multiple nested depressions, indicating that collapse occurred in several separate events. The depth of the caldera reaches about 3 kilometers, meaning that the highest point on Olympus Mons is actually at the rim of the caldera rather than at its center. The nested structure suggests a long history of volcanic activity, with different episodes of eruption and collapse creating the layered features visible today. The flanks of the volcano display numerous flow features visible in high-resolution imagery. Lava flows radiate from the summit down the slopes, their margins clearly defined where the flow boundaries froze. Some flows show levees, raised edges that formed as the surface of the flow cooled, while molten lava continued to travel down the center channel. Other flows display ropey textures characteristic of Pahoho lava, where the thin solidified crust wrinkled as the flowing lava beneath continued to move. These features provide evidence of the fluid nature of the eruptions that built Olympus Mons. Around the base of the volcano, a steep scarp rises several kilometers high, forming a cliff that encircles much of the mountain. This escarpment, called the basal scarp, has provoked discussion among planetary geologists. Some suggest it formed through erosion or mass wasting, the gradual collapse of the volcano's lower slopes. Others propose that it represents the edge of the lava flows, marking where the mountain ends and the surrounding terrain begins. The scarp is not continuous around the entire base, and its height varies, reaching up to 7 kilometers in some locations. Beyond the basal scarp lies an aureole, a region of distinctive terrain that surrounds Olympus Mons. The aureole consists of large blocks and ridges of material that appear to have slid away from the main volcanic edifice. The texture resembles debris from massive landslides, suggesting that portions of the volcano's flanks may have collapsed at various times, creating the jumbled terrain now visible in the aureole deposits. These features extend hundreds of kilometers from the base of the mountain, indicating that the collapse events were enormous in scale. The formation of Olympus Mons required conditions unique to Mars. The lower gravity on Mars, about 38% of Earth's gravity, allowed lava to flow further before cooling and permitted the volcano to grow taller before its own weight caused structural failure. On Earth, the weight of such a massive volcano would cause the crust beneath it to sink and deform, limiting the ultimate height the mountain could reach. On Mars, the cooler lithosphere and lower gravity allow the crust to support more weight, enabling the construction of larger volcanic edifices. Another critical factor is the lack of plate tectonics on Mars. On Earth, the Hawaiian Islands formed as the Pacific Plate moved over a stationary hotspot in the Ure mantle, creating a chain of volcanoes that progressively increase in age along the chain. Each volcano was active only while it sat over the hotspot, then became extinct as the plate carried it away and a new volcano formed in its place. On Mars, the crust does not move laterally over the mantle. A hotspot beneath the surface can remain in one location for billions of years, continuously feeding lava to the same volcano and allowing it to grow to enormous size. The age of Olympus Mons remains uncertain, but is likely measured in hundreds of millions of years, possibly reaching back more than 1 billion years. The relatively smooth flanks with few impact craters suggest that at least some surfaces on the volcano are geologically young by Martian standards, perhaps only a few 100 million years old. This implies that Olympus Mons may have been active relatively recently in geological terms, though no evidence exists for current volcanic activity. The volcano may be dormant rather than extinct, potentially capable of erupting again in the future if magma still exists in chambers beneath the mountain. Scientists have identified possible lava tubes on the flanks of Olympus Mons, channels where lava once flowed beneath a solidified crust. When the eruption ended and the lava drained away, these channels were left as hollow tunnels beneath the surface. Some appear to have collapsed in places, creating chains of pit craters that mark the former routes of subsurface lava flows. These tubes, if intact, could provide natural shelter from radiation and temperature extremes, features that make them interesting from the perspective of potential future exploration. The summit of Olympus Mons extends above much of the Martian atmosphere. At an elevation of 21.9 kilometers, the atmospheric pressure at the peak is approximately 72 pascals, about 12% of the mean surface pressure. This is so low that it approaches the vapor pressure of water. Ice, meaning that any water ice exposed at the summit would sublime rapidly into the thin air. The low pressure also means that the diurnal temperature range at the summit is even more extreme than at lower elevations, with temperatures swinging by perhaps 60 or 70 degrees between day and night. From the summit of Olympus Mons, the view would be extraordinary, though not in the ways one might expect. Looking outward, the horizon would appear much closer than it does on Earth due to the smaller radius of Mars. The planet curves away more sharply, limiting the distance one can see. However, from such a great height, the horizon would still be several hundred kilometers away. The surrounding landscape would spread out in all directions, the reddish-brown terrain stretching to the limits of visibility. To the east, one might see the other large volcanoes of the Tharsis region, though atmospheric dust would likely obscure distant features. Looking upward from the summit, the sky would appear darker than at lower elevations due to the thinness of the atmosphere at that altitude. During the day, the butterscotch color typical of the Martian sky would deepen toward a darker brown or even approach black, similar to the view from high-altitude aircraft on Earth. Stars might be visible even during daylight hours, scattered points of light showing through the thin veil of atmosphere. The Sun would appear about 2/3 the size it appears from Earth, a consequence of Mars's greater distance from our star. The Tharsis region, where Olympus Mons is located, hosts 3 other large shield volcanoes: Arsia Mons, Pavonis Mons, and Ascraeus Mons. These 3 volcanoes sit in a roughly linear arrangement stretching northeast from Olympus Mons. All are substantial mountains in their own right, with heights ranging from about 14 to 18 kilometers. Together with Olympus Mons, they form a volcanic province that dominates an entire hemisphere of Mars. The Tharsis Bulge itself, the broad elevated region that contains these volcanoes, rises several kilometers above the surrounding terrain and spans approximately 5,000 kilometers across. The existence of such massive volcanic features on Mars provides evidence of significant internal heat during the planet's history. Volcanism requires molten rock, and the production of magma requires heat to melt the mantle. Mars, being smaller than Earth, lost its internal heat more rapidly after formation. Yet the large volcanoes demonstrate that Mars remained volcanically active for an extended period, possibly continuing until relatively recently. The heat to drive this volcanism likely came from radioactive decay of elements like uranium, thorium, and potassium in the Martian interior, supplemented by residual heat from the planet's formation. Olympus Mons and the other Tharsis volcanoes may have influenced the global climate of Mars. During periods of active eruption, these volcanoes would have released gases into the atmosphere, including water vapor, carbon dioxide, and sulfur compounds. Large eruptions could have temporarily thickened the atmosphere and altered the climate, possibly even creating conditions where liquid water could exist on the surface for brief periods. The total volume of lava erupted to build these volcanoes is enormous, and the associated gas emissions would have been substantial, potentially playing a role in shaping the Martian environment. The mountain stands now in silence. Its eruptions ceased for millions or hundreds of millions of years. No lava flows from its vents, no gases escape from its summit. The caldera sits empty and cold, a frozen landscape at the top of the solar system's tallest mountain. Wind carries dust across the slopes, accumulating in some areas and eroding others. The thin atmosphere provides minimal protection from the rain of micrometeorites that constantly strike the surface, very gradually eroding the rock. The mountain changes, but at a pace so slow as to be imperceptible on human timescales. If volcanism were to resume on Olympus Mons, the eruptions would likely resemble those that built the mountain originally. Basaltic lava would flow from vents at the summit or on the flanks, spreading across the surface in sheets and channels. The low viscosity would allow the lava to travel long distances, perhaps tens of kilometers, before cooling and solidifying. Gas would bubble from the molten rock, releasing volatiles into the atmosphere. The eruption might continue for months or years, adding new layers to the ancient structure. Then it would stop, and the mountain would return to its dormant state. But no such eruption appears likely in the near future. The planet has cooled. Its interior, while still retaining some heat, no longer generates magma at the rates it once did. The age of great volcanism on Mars has passed. What remains is the record of that age, preserved in the massive shields that still dominate the landscape. Olympus Mons is a monument to a more active era, a time when Mars was a volcanic world on a scale that Earth has never approached. The mountain will stand for billions of years to come, slowly eroding grain by grain, but retaining its essential form long after human civilization has ended. If Olympus Mons represents vertical grandeur, Valles Marineris embodies horizontal vastness. This canyon system stretches across nearly 1/4 of Mars's circumference, extending approximately 4,000 kilometers from west to east. To put this in perspective, if Valles Marineris were placed on Earth, it would span the entire width of the continental United States from coast to coast. The Grand Canyon in Arizona, often considered Earth's most impressive canyon, measures only 446 kilometers long, about 1/9 the length of Valles Marineris. The depth of Valles Marineris reaches 7 kilometers at its deepest point, measured from the surrounding plateau down to the canyon floor. This depth is several times greater than the depth of the Grand Canyon, which reaches about 1.8 kilometers at its deepest. The width varies along the length of the canyon system, ranging from about 100 kilometers in the narrower eastern sections to 600 kilometers in the central portion where several parallel canyons merge. In these wide sections, if you stood on one rim of the canyon, the opposite rim would be beyond the horizon, invisible due to the curvature of Mars. Valles Marineris is not a single canyon but a complex system of interconnected troughs and depressions. The main canyon runs roughly east-west, parallel to the Martian equator, but numerous tributary canyons branch off to the north and south. These tributaries have their own names: Eus Chasma, Tithonium Chasma, Ophir Chasma, Candor Chasma, Melas Chasma, Coprates Chasma, and many others. Each represents a distinct geological feature with its own characteristics, but all connect to form the larger network that constitutes Valles Marineris. The formation of Valles Marineris differs fundamentally from the formation of canyons on Earth. The Grand Canyon formed through the erosive action of the Colorado River cutting downward through layers of rock over millions of years. Valles Marineris did not form through water erosion. Instead, it is a tectonic feature created by faulting and collapse of the Martian crust. The canyon system sits on the eastern flank of the Tharsis Bulge, the massive elevated region that hosts Olympus Mons and the other large volcanoes. As the Tharsis region rose, possibly due to upwelling in the mantle or the accumulation of volcanic material, the surrounding crust stretched and cracked. This stretching created zones of weakness where the crust pulled apart. Along these zones, normal faults developed, fractures where one block of crust dropped down relative to another. As faulting continued, the dropped blocks subsided further, creating the deep troughs that became Valles Marineris. The process resembled the formation of rift valleys on Earth, places like the East African Rift, where continental crust is being pulled apart by tectonic forces. However, the scale of Valles Marineris far exceeds any rift valley on Earth, a consequence of the massive size of the Tharsis Bulge and the stresses its formation imposed on the surrounding crust. The walls of Valles Marineris display layered rock formations visible in high-resolution orbital imagery. These layers record the geological history of Mars, deposited over billions of years as sediments, volcanic materials, and possibly other substances accumulated on the surface. Different layers have different colors and textures, suggesting variations in composition or grain size. Some layers appear more resistant to erosion than others, creating steppe topography where harder layers project outward from the cliff face while softer layers recede. Landslides have carved into the canyon walls in many locations. Massive rockfalls and debris avalanches have detached from the cliffs and tumbled down to the canyon floor, creating fan-shaped deposits that spread out below the source areas. Some of these landslides are among the largest known in the solar system, with volumes measured in thousands of cubic kilometers. The deposits display distinctive morphology, with longitudinal ridges and grooves aligned parallel to the direction of flow, features that suggest the debris moved rapidly, perhaps lubricated by trapped air or even ice within the failing rock mass. The floors of the canyons contain layered deposits distinct from the material exposed in the canyon walls. These interior layered deposits, as they are called, consist of alternating light and dark layers that can extend for tens or hundreds of kilometers. The composition of these deposits remains uncertain. Some researchers suggest they formed from sediments, deposited by wind, with different layers representing different episodes of deposition or variations in grain size. Others propose that the deposits formed from volcanic ash that settled into the canyons, or from minerals that precipitated from water if the canyons once held lakes. Evidence for water in Valle Marineris remains ambiguous but intriguing. Some channels appear to lead into the canyons from the surrounding plateaus, suggesting that water may have flowed into the canyons at some point in Martian history. The eastern end of Valles Marineris transitions into chaotic terrain and outflow channels that clearly formed through catastrophic floods of water. These outflow channels suggest that enormous quantities of groundwater were released suddenly, perhaps when underground ice melted or when confined aquifers breached to the surface. Whether water ever ponded in the canyons themselves, forming temporary lakes, remains uncertain. The depth and length of Valles Marineris create dramatic vertical relief and variations in atmospheric pressure. At the bottom of the deepest canyons, the atmospheric pressure is significantly higher than on the surrounding plateaus, perhaps 30 to 40% higher. This increased pressure results from the weight of the atmosphere above, the same principle that makes air pressure higher at lower elevations on Earth. The increased pressure at the bottom of the canyons could theoretically allow water to exist in liquid form at temperatures where it would freeze or sublime at higher elevations, though the temperatures would still need to be relatively warm for liquid water to be stable. Clouds form within Valles Marineris, visible in images taken during the Martian morning. These clouds consist of water ice crystals that condense from atmospheric moisture as temperatures cool overnight. The topography of the canyon system influences atmospheric circulation, creating local wind patterns that can concentrate moisture in certain areas. As the sun rises and temperatures increase, the clouds typically dissipate, subliming back into water vapor. The process repeats the following night, a daily cycle that continues throughout the Martian year. The canyon walls show evidence of ongoing erosion and modification. Gullies appear on some slopes, narrow channels that suggest downslope movement of material. The origin of these features remains debated, with proposals ranging from dry granular flows to flows involving liquid water or brines. Some gullies show evidence of recent activity, with fresh-looking deposits that contain few impact craters, suggesting formation within the past few million years or even more recently. The vast scale of Valles Marineris makes it a dominant feature in any global view of Mars. Images of the full disk of the planet often show the canyon system as a dark scar across the face of the world, stretching nearly a quarter of the way around the equator. The visual impact of the feature is striking even from millions of kilometers away in space. From the surface, standing at the rim of one of the main canyons, the view would be incomprehensible in its scale. The opposite wall would be invisible beyond the horizon. The floor would lie 7 kilometers below, further down than the highest peaks on Earth rise above sea level. If you descended from the rim to the floor, the journey would take you through exposed layers representing perhaps billions of years of Martian history. Each layer would tell part of the story of the planet's past, recording conditions at the surface when that material was deposited. The rocks would show variations in color and texture, evidence of different processes and different environments. Near the bottom, you might encounter the interior layered deposits, mysterious materials that hint at past climates and conditions different from today. The temperature at the bottom of the canyon would be noticeably warmer than at the rim during the day, a consequence of the increased atmospheric pressure and reduced altitude. The temperature difference might reach 10 or 20 degrees Celsius, substantial on a planet where temperatures are generally very cold. At night, however, the low thermal inertia of the thin atmosphere and dry surface would allow heat to radiate away rapidly, and temperatures would plunge, perhaps approaching the same low values found at the rim. Wind funnels through the canyons, accelerated by the topography. During dust storm season, when atmospheric disturbances sweep across the planet, wind speeds in the canyons can increase substantially as air is forced through the narrow passages between the walls. Dust lifted from the canyon floors and slopes can fill the interior of the canyons, reducing visibility and creating a hazy environment. When the storms subside, the dust gradually settles, coating surfaces with a fresh layer of fine particles. The canyons influence the distribution of dust across Mars. Material eroded from the canyon walls accumulates on the floors and is then available to be lifted by wind and transported elsewhere. Some of this dust may be carried out of the canyon system entirely, contributing to the global dust loading in the atmosphere. Other material may be moved within the canyon system, redistributed from one area to another. The net effect is a slow redistribution of material, a geological process that continues today at rates measurable over decades with careful observation. Valles Marineris represents one of the most significant tectonic features on any terrestrial planet in the solar system. Its formation required forces capable of fracturing and displacing enormous volumes of crustal rock. The stresses that created the canyon system operated over extended periods, likely millions of years, progressively opening the canyons as the crust stretched and faulted. The feature stands as evidence that Mars, despite its small size and apparent inactivity today, experienced powerful geological processes in its past. The canyon system will continue to evolve slowly through ongoing erosion and mass wasting. Rockfalls will detach from the walls, gradually widening the canyons and reducing the height of the cliffs. Wind will transport material from some areas and deposit it in others, slowly filling portions of the canyon floors while eroding other areas. The processes are slow, measured in millimeters or centimeters per millennium, but they continue nonetheless. Millions of years from now, Valles Marineris will look different in detail, though its fundamental structure will remain recognizable. The canyon exists as a permanent feature of the Martian landscape, carved by ancient forces that no longer operate with the same intensity. It will remain as long as Mars retains its current form, a monument to the tectonic activity that once shaped the planet. The walls will slowly erode, The floors will gradually fill, but the essential character of the canyon system will persist for billions of years, a vast scar across the face of a red world, testament to the power of geological forces operating over immense timescales. Dust defines much of the Martian experience. It covers the surface in most locations, a layer of fine particles that have been ground down over billions of years through impact fragmentation, weathering, and wind transport. The dust particles average about 1.5 micrometers in diameter, smaller than the width of a human hair, small enough to remain suspended in the atmosphere for extended periods once lifted aloft. The composition consists primarily of iron oxide minerals, the rust-like compounds that give Mars its distinctive red color, along with varying amounts of silicon dioxide, magnesium, aluminum, calcium, and other elements. The presence of dust in the atmosphere affects nearly every aspect of Martian weather and climate. Even during the clearest conditions, some dust remains suspended, giving the sky its characteristic butterscotch hue. This airborne dust absorbs and scatters sunlight, redistributing solar energy within the atmosphere. It acts as condensation nuclei for water ice and carbon dioxide ice crystals, enabling cloud formation. It influences atmospheric temperature structure, creating layers where temperature increases with altitude rather than decreasing, opposite to the normal pattern. These temperature inversions affect atmospheric stability and the development of winds. The amount of dust in the atmosphere varies dramatically with season and from year to year. During much of the Martian year, dust loading remains relatively low, with optical depth values between 0.1 and 0.5. Under these conditions, the atmosphere is relatively transparent, allowing good visibility and strong solar heating of the surface. But during the southern spring and summer, when Mars passes through perihelion and receives maximum solar energy, the frequency and intensity of dust storms increases. Local storms can lift dust into the atmosphere, and under the right conditions, these storms can expand and merge, sometimes developing into planet-encircling events. Global dust storms occur on Mars irregularly, typically once every 3 to 4 Martian years, though the exact timing remains unpredictable. During these events, dust spreads across the entire planet, raising optical depth values to 10 or higher. Sunlight reaching the surface drops to a few percent of normal levels, comparable to heavy overcast conditions on Earth. The sky turns opaque, obscuring the sun except as a diffuse glow. Surface temperatures drop during the day because less solar energy reaches the ground, while atmospheric temperatures increase as the suspended dust absorbs sunlight. These global events can last for weeks or even months before the dust begins to settle out of the atmosphere. The storms of 1971 and 2018 rank among the most intense observed, with 2018's storm completely obscuring the surface from orbital view for several weeks. The Opportunity rover, which was exploring Mars at the time, lost contact as its solar panels were covered with dust and deprived of sunlight. The rover never recovered after the storm cleared, ending a mission that had lasted more than 14 years. The mechanisms that trigger global dust storms remain incompletely understood. Local and regional storms occur regularly throughout the Martian year, but most remain confined to limited areas and dissipate after a few days. What causes some storms to expand into planet-wide events? Current understanding suggests that positive feedbacks play a crucial role. When dust is lifted into the atmosphere, it absorbs sunlight and warms the air. This warming increases atmospheric instability and can strengthen winds, which lift more dust, which warms the air further, creating a self-reinforcing cycle. If this feedback becomes strong enough, the storm can continue to grow until dust covers the entire planet. The timing of global storms shows a preference for southern spring and summer, the period when Mars is near perihelion. The increased solar energy reaching the planet during this season provides more energy to drive atmospheric circulation. The stronger winds associated with this enhanced circulation can more easily lift dust from the surface. Additionally, during southern summer, the sublimation of the seasonal carbon dioxide cap at the South Pole creates strong pressure gradients and winds that blow outward from the pole. These winds can trigger dust storms in the region around the retreating ice cap. Smaller-scale dust lifting occurs continuously across Mars through the action of dust devils. These are rotating columns of air, similar in structure to the dust devils seen in deserts on Earth, though typically larger and taller. Martian dust devils can reach heights of several kilometers with diameters of tens to hundreds of meters. They form when the surface heats during the day, creating parcels of warm air that rise through the cooler atmosphere above. If conditions are right, these rising parcels can acquire rotation, creating a vortex that moves across the surface, lifting dust as it goes. Dust devils are visible in images from orbit as dark or light tracks across the Martian surface. The tracks form because the vortex removes the uppermost layer of dust, either revealing darker material beneath or depositing brighter dust depending on local conditions. Thousands of these tracks can be seen in high-resolution images of certain regions. Landers and rovers have directly observed dust devils passing nearby, capturing them in images and sometimes detecting the pressure drop associated with the low-pressure center of the vortex. The movement of dust devils across the surface provides an important cleaning mechanism for solar panels on Martian spacecraft. Dust settles on solar panels over time, reducing their efficiency by blocking sunlight. But when a dust devil passes over a lander or rover, the wind can blow dust off the panels, temporarily increasing power output. Both the Spirit and Opportunity rovers experienced these cleaning events multiple times during their missions, extending their operational lifetimes by restoring solar panel performance. Regional dust storms occur more frequently than global events, but less commonly than isolated local storms. These regional storms can cover areas equivalent to large portions of continents on Earth, raising dust over millions of square kilometers. They typically last several days to a few weeks before dissipating. The storms follow preferred regions and seasons, often developing near the retreating edge of the seasonal carbon dioxide caps where strong winds blow and loose dust is abundant. The dust in the Martian atmosphere eventually settles back to the surface through sedimentation. In the absence of ongoing lifting, atmospheric dust would fall out completely in a matter of weeks to months. The tiny particles fall slowly through the thin atmosphere, their descent governed by the balance between gravitational pull and aerodynamic drag. Larger particles settle faster than smaller ones, creating a size-dependent distribution of dust in the atmosphere with altitude. The smallest particles remain suspended longest, particularly if any vertical mixing or turbulence keeps them aloft. When dust settles onto the surface, it blankets the terrain in a uniform layer. This deposition gradually obscures surface features, filling in small-scale topography and creating the smooth, dust-covered plains visible in many regions. Over geological time, the accumulation of wind-blown dust has created layered deposits meters to tens of meters thick. Some of these deposits show regular layering with rhythmic variations in properties, possibly reflecting climate cycles driven by changes in Mars's orbital parameters and axial tilt. The dust storms of Mars serve as a reminder that the planet remains active, that weather continues to reshape the surface, and that the thin atmosphere, despite its low pressure, can generate forces sufficient to move material across global scales. The storms do not approach the violence of hurricanes or tornadoes on Earth, as the low atmospheric density limits the forces that winds can exert. But the persistence of the winds and their ability to operate across the entire planet create an environment where dust transport remains one of the dominant surface processes. In between storms, during the clear periods that make up much of the Martian year, dust still moves across the surface, just at lower rates. Local winds lift particles and carry them short distances before they settle again. Dust devils trace their paths across plains and slopes, temporarily lofting dust into the air. The process is gentle but continuous, a slow redistribution of material that never truly stops. The surface is never entirely still, never completely inactive. Some grain of dust is always in motion somewhere on Mars, carried by wind that never ceases. The red color of Mars, visible from Earth with the naked eye, and the source of the planet's association with blood and war in many ancient cultures, results entirely from this dust and the oxidized iron it contains. If the dust were swept away, if the surface could be cleaned down to bare rock, the planet might appear darker, perhaps gray or brown depending on the composition of the underlying material. But the dust cannot be removed. It is an integral part of the Martian environment, produced by the breakdown of rocks over billions of years, redistributed by wind and destined to remain for billions more. The dust settles onto everything. Landers and rovers gradually accumulate coatings that change their appearance over time. Rocks slowly disappear beneath layers of fine particles. Impact craters fill in as dust drifts into their bowls. Ancient surface features become muted and indistinct under the blanket of uniform material. Yet, in other areas, wind scours the surface, removing dust and creating regions where bedrock or older layered deposits remain exposed. The competition between deposition and erosion creates the varied landscape visible today. Some regions buried in dust, others swept clean. This quiet redistribution of material will continue as long as Mars retains its atmosphere. The storms will rise and fall. Dust will lift and settle. The surface will change in detail while remaining fundamentally the same, covered in rust-colored particles that give the planet its identity, its character, its particular shade of red that makes it immediately recognizable among the worlds of the solar system. Mars has 2 moons, but neither resembles Earth's moon in any significant way. Phobos and Deimos are small, irregular bodies, more akin to asteroids than to the large, spherical satellites that orbit the giant planets. Their names come from Greek mythology. Phobos represents fear, and Deimos represents panic or dread, both appropriate attendants for Mars, the god of war. The moons were predicted before they were discovered, with Jonathan Swift's satirical work, Gulliver's Travels, mentioning 2 Martian moons more than a century before their actual detection, though Swift's description was pure invention. The real moons were discovered in August 1877 by Asaph Hall using the 26-inch refracting telescope at the United States Naval Observatory in Washington, D.C. Hall had nearly given up his search when his wife encouraged him to continue for one more night. On that night, he detected Deimos, and 6 days later, he found Phobos. The discovery confirmed what some astronomers had suspected, that Mars, positioned between the asteroid-rich region beyond and the moon-orbited Earth within, might reasonably be expected to have small satellites. Phobos, the larger and inner of the 2 moons, measures approximately 27 kilometers in its longest dimension, 22.2 kilometers in its intermediate dimension, and 18.4 kilometers in its shortest dimension. This irregular shape results from the Moon's insufficient mass to pull itself into a sphere through gravitational self-compression. Objects smaller than about 200 to 300 kilometers in diameter typically lack enough gravity to overcome the mechanical strength of rock, leaving them in whatever irregular form resulted from their formation and subsequent collision history. The surface of Phobos is heavily cratered, evidence of a long history of impacts by smaller bodies. The most prominent feature is Stickney Crater, a massive impact scar measuring approximately 9 kilometers in diameter, about 40% the width of Phobos itself. The impact that created Stickney must have come close to shattering Phobos entirely, and indeed, fractures and grooves radiate across the surface from the crater, possibly formed by the shock waves from the impact. The survival of Phobos after such an impact suggests that the Moon may have significant structural strength, or possibly that it is a fractured rubble pile held together by gravity, able to absorb impacts through the reorganization of its components. Grooves cover much of Phobos's surface, linear depressions tens to hundreds of meters wide and generally parallel to one another. The origin of these grooves has generated considerable discussion. Early hypotheses suggested they formed from the Stickney impact, but their alignment does not consistently support this interpretation. More recent proposals suggest they result from rolling boulders ejected from impacts or from tidal stress, as Mars's gravity pulls on the asymmetric mass distribution of Phobos. The grooves might also relate to the gradual structural failure of the Moon as tidal forces cause it to spiral inward toward Mars. Phobos orbits Mars at an average distance of approximately 9,376 kilometers from the planet's center, which is about 6,000 kilometers above the Martian surface. This places it closer to its planet than any other known moon in the solar system relative to the size of the primary body. The orbital period is 7 hours 39.2 minutes, meaning that Phobos completes more than 3 orbits of Mars in a single Martian day. For an observer on the Martian surface, Phobos would rise in the west and set in the east, opposite to the normal pattern, because its orbital period is shorter than Mars's rotation period. The tidal interactions between Mars and Phobos cause the Moon to gradually spiral inward. Tidal forces from Mars create a bulge in Phobos, and as the Moon rotates relative to this bulge, friction dissipates energy, slowing the Moon's orbital motion. This loss of orbital energy causes Phobos to drop closer to Mars at a rate of approximately 1.8 centimeters per century. The process is slow but relentless, and it will eventually lead to the Moon's destruction. Current estimates suggest that Phobos will reach its end in approximately 30 to 50 million years, though some studies propose shorter timeframes. As the Moon spirals inward, it will eventually cross what is called the Roche limit, the distance at which Mars's tidal forces become stronger than Phobos's own gravity holding it together. At this point, estimated to occur when Phobos reaches an orbital altitude of approximately 3,620 kilometers above the Martian surface, the Moon will begin to break apart. The fragments will spread out along its orbit, forming a ring around Mars. This ring will be temporary on geological timescales, gradually dispersing as pieces fall into the planet or are ejected from orbit. The grooves on Phobos's surface may already show evidence of this. Gradual dismemberment. While scientists initially attributed these features to the Stickney impact, more recent analysis suggests they may be stress fractures created by tidal forces. As Mars's gravity deforms Phobos, the strain builds up in the Moon's structure. The interior of Phobos appears to be porous and weak, possibly a loosely consolidated pile of rubble surrounded by a layer of finer material. Such a structure would allow tidal forces to create internal deformation, resulting in surface cracks that show up as the parallel grooves visible in images. Deimos, the outer and smaller moon, follows a different trajectory. It orbits beyond the synchronous orbit distance, the altitude at which an orbit takes exactly as long as Mars's rotation period. At this distance and beyond, tidal interactions transfer angular momentum from Mars to the Moon, causing Deimos to slowly move away from the planet rather than inward. The rate of this recession is very slow, measured in fractions of a centimeter per year, but over millions of years it accumulates. Deimos will gradually drift outward, eventually perhaps escaping Mars's gravity entirely if given enough time, though this would require timescales much longer than the projected destruction of Phobos. Deimos measures approximately 12.6 kilometers in its longest dimension, 7.4 kilometers in intermediate, and 6.2 kilometers in its shortest dimension. Like Phobos, it is irregularly shaped and too small for gravity to compress it into a sphere. Its surface is smoother than that of Phobos, with fewer large craters and more extensive coverage of fine-grained regolith, the dust and soil that accumulates through micrometeorite impacts and space weathering. The regolith layer on Deimos may be several tens of meters thick, possibly explaining why fewer craters are visible. Impacts may simply bury themselves in the loose material without creating distinct crater rims. The orbital period of Deimos is 30.35 hours, meaning it takes more than a Martian day to complete one orbit. For an observer on the Martian surface, Deimos would rise in the east and set in the west, following the normal pattern, unlike the retrograde apparent motion of Phobos. However, Deimos would appear very small in the Martian sky, only about 1 to 2 arc-minutes across, similar to the apparent size of Venus as seen from Earth. It would look like a bright star or planet rather than a disk, insufficient to cast noticeable shadows or create recognizable transits across the Sun. The origin of both moons remains uncertain despite decades of study. Their composition and physical properties resemble those of carbonaceous asteroids found in the outer asteroid belt, suggesting they might be captured asteroids. However, their nearly circular orbits lying precisely in Mars's equatorial plane argue against simple capture, which would typically produce highly elliptical or inclined orbits. Some mechanism would need to have circularized the orbits and adjusted their inclinations, possibly through interaction with a thicker early Martian atmosphere or through tidal forces operating over extended periods. An alternative hypothesis proposes that Phobos and Deimos formed from debris ejected into orbit around Mars by a massive impact early in the planet's history. In this scenario, a large body struck Mars with enough energy to loft material into orbit, similar to the giant impact that is thought to have formed Earth's moon. The debris would have formed a disk around Mars, and over time, this disk would have coalesced into one or more moons. Evidence from computer simulations suggests that if Phobos and Deimos share a common origin, they may be the remnants of a larger moon that was disrupted between 1 and 2.7 billion years ago, possibly through collision with another object. Recent analysis using data from NASA's InSight lander, which detected seismic signals and tidal deformations on Mars, has provided new constraints on the orbital evolution of the moons. By measuring how Mars responds to the gravitational pull of Phobos, scientists can determine properties of the planet's interior and refine estimates of how the moon's orbit has changed over time. These measurements support the idea that Phobos and Deimos share a common origin and that their orbits have evolved significantly since their formation. Regardless of their origin, both moons exist in their current orbits following the same physical laws that govern all orbital motion. They circle Mars with mathematical precision, their paths determined by the balance between gravitational attraction and orbital velocity. Phobos completes 3 full orbits in less time than it takes Mars to rotate once. Deimos takes longer, serenely circling the planet while Mars spins beneath it. The 2 moons never interact directly, their orbits too far separated for gravitational perturbations to significantly affect one another. The surfaces of both moons are ancient and heavily modified by impacts. Every crater records a collision with a smaller object, marking the surface with scars that persist for billions of years in the absence of erosion or geological activity. The lack of atmosphere on the moons means that no wind or weather can smooth these features. The lack of water means no erosion from flow or ice. The lack of tectonic activity means no volcanism or crustal movement to resurface the terrain. What exists on the surfaces of Phobos and Deimos is the accumulated record of billions of years of impacts, modified only by the gradual accumulation of more impact debris and the weathering caused by solar radiation and micrometeorite bombardment. Both moons are tidally locked to Mars, meaning they rotate at the same rate as they orbit, keeping one face permanently pointed toward the planet. This configuration results from the same tidal forces that cause the moons: orbital evolution. Over time, tidal friction slows a moon's rotation until it matches its orbital period, creating a stable configuration where the tidal bulge raised by the planet always points in the same direction. Earth's moon is similarly locked to Earth, always showing the same face. Most large moons in the solar system are tidally locked to their planets. For an observer standing on the Mars-facing side of Phobos, Mars would dominate the sky, appearing about 40 degrees across, more than 80 times the apparent diameter of the moon as seen from Earth. The planet would hang motionless in the same position in the sky, never rising or setting, slowly cycling through phases as Phobos orbited and different portions of Mars reflected sunlight. The view would be spectacular, showing the polar ice caps, the major volcanic features, the canyon systems, and the dust storms as they developed and dissipated. On the far side of Phobos, the side that never faces Mars, the planet would never be visible. The sky would contain only the sun, significantly smaller and dimmer than it appears from Earth, and the distant stars. The sun would rise and set with Phobos's orbital period, creating a day-night cycle lasting about 7.65 hours. Deimos, while visible from certain locations on Phobos, would appear as only a small point of light, too distant to show any detail to the naked eye. The future of both moons is determined by orbital mechanics and tidal forces. Phobos will continue its inward spiral, accelerating as it approaches Mars until tidal forces tear it apart. The debris will form a ring that will gradually disperse. Deimos will continue its slow outward drift, gradually receding from Mars over millions of years. Both futures are certain, written in the mathematics of orbital dynamics and gravitational interaction. The timescales involved are long compared to human experience, but brief in geological terms. These 2 small moons, irregular chunks of rock orbiting a red planet, continue their ancient dance through space. They circle endlessly, falling and rising, approaching and receding, governed by forces they cannot resist. They exist as they have existed for billions of years and will exist for millions more, companions to a planet that itself spins through the darkness, all of them following the invisible lines of gravitational fields that define their paths through the cosmos. The surface of Mars experiences temperature extremes that result from the planet's thin atmosphere, low thermal inertia, and varying distance from the Sun. Understanding these temperature variations provides insight into the environment that exists on the planet and the processes that shape its surface. The temperatures encountered on Mars range from pleasantly warm by human standards to cold enough to freeze carbon dioxide, creating conditions unlike anywhere on Earth. The average surface temperature on Mars is approximately -63 degrees Celsius, though this figure obscures significant variations with latitude, season, time of day, and elevation. At the equator during summer, temperatures can reach as high as 20 degrees Celsius at noon, similar to a mild spring day in temperate regions on Earth. However, these warm temperatures occur only during the middle of the day in the warmest season and only in direct sunlight. Move into shadow, wait a few hours for sunset, or travel to higher latitudes and the temperature drops dramatically. At night, even at the equator during summer, temperatures plunge to around -73 degrees Celsius. This daily temperature swing of more than 90 degrees results from the thin atmosphere's inability to retain heat. During the day, sunlight warms the surface directly. The ground heats up, sometimes reaching temperatures above freezing, even when the air temperature remains well below zero. But at night, with no sun to provide energy, the surface radiates its heat away into space. The thin atmosphere cannot hold this heat, and within hours of sunset, the ground cools to frigid temperatures. The diurnal temperature range, this daily swing from warm to cold, is one of the most striking features of Martian climate. On Earth, even in deserts where the air is dry and the sky is clear, the temperature swing rarely exceeds 20 to 30 degrees. Mars experiences swings 3 to 4 times larger as a matter of routine. Measurements from NASA's Viking landers, which operated on Mars in the late 1970s, recorded air temperatures ranging from +1 degree Celsius to -107 degrees Celsius over the course of the mission. The warmest measurements typically occurred during midday in summer, while the coldest occurred at night in winter. More recent measurements from the Spirit rover, which operated near the equator in Gusev crater, recorded a maximum daytime air temperature in the shade of 35 degrees Celsius, remarkably warm by Martian standards. The rover regularly measured temperatures above freezing during the warmest parts of summer days, though these warm conditions lasted only a few hours before the temperature began to fall again. At night, temperatures dropped to typical Martian lows, well below freezing, creating a harsh environment that alternated between relatively moderate and extremely cold every single day. The warmest soil temperatures measured on Mars, detected by the Viking orbiter using infrared instruments, reached approximately 27 degrees Celsius. These measurements represent the temperature of sun-exposed surfaces during the warmest conditions, likely occurring during summer at low latitudes around local noon. The soil can become significantly warmer than the air above it because the ground absorbs sunlight directly while the thin atmosphere does little to block solar radiation or trap heat. At the opposite extreme, the polar regions experience temperatures cold enough to freeze carbon dioxide. During winter, the temperature at the poles drops to approximately -153 degrees Celsius. At these temperatures, carbon dioxide gas in the atmosphere condenses directly onto the surface, forming dry ice. This is the same process that allows the seasonal polar caps to grow during winter, pulling mass from the atmosphere and depositing it as solid carbon dioxide on the existing ice caps. Temperature varies significantly with elevation on Mars due to changes in atmospheric pressure and surface conditions. Higher elevations experience lower pressures and often colder temperatures, Though the relationship is complex and affected by factors like surface albedo, thermal inertia of the soil, and atmospheric dust content. At the summit of Olympus Mons, the temperature rarely rises above -100 degrees Celsius, even during summer, while in the depths of Hellas Planitia, temperatures can be notably warmer than surrounding regions at similar latitudes. The seasonal variation in temperature follows the pattern set by Mars's axial tilt and eccentric orbit. During southern summer, when Mars is near perihelion and the southern hemisphere tilts toward the Sun, that hemisphere experiences its warmest temperatures. However, these temperatures are often moderated by dust storms that obscure the Sun and reduce the amount of solar energy reaching the surface. During northern summer, when Mars is near aphelion and receiving less total solar energy, the northern hemisphere still warms considerably, often more so than the southern hemisphere in its summer because of the lower likelihood of major dust storms. Dust storms themselves have profound effects on temperature. During a global dust storm, when dust fills the atmosphere and blocks much of the sunlight from reaching the surface, daytime surface temperatures drop significantly, sometimes by 20 degrees or more. At the same time, atmospheric temperatures increase because the suspended dust absorbs sunlight directly. The normal daytime-nighttime temperature swing narrows considerably during dust storms, from typical swings of 50 degrees or more down to perhaps 10 to 15 degrees. The atmosphere becomes more uniform in temperature, though colder overall at the surface and warmer at altitude. The Viking landers observed a global dust storm firsthand. Within an hour of the storm's arrival at their location, wind speeds increased substantially, reaching 17 meters per second with gusts up to 26 meters per second. The diurnal temperature range dropped sharply from about 50 degrees to approximately 10 degrees. Despite these strong winds, the landers did not observe any transport of large particles at the surface, only a gradual brightening and loss of contrast as fine dust settled onto everything. The low atmospheric density means that even wind speeds that sound substantial by Earth standards exert relatively weak forces on surface materials. After a global dust storm subsides and the dust begins to settle out of the atmosphere, temperatures return gradually to their normal patterns. The settling process can take weeks or months, during which the optical depth of the atmosphere slowly decreases and more sunlight reaches the surface. As solar heating of the ground increases, daytime temperatures rise. The nighttime temperatures may take longer to recover as the atmosphere needs to thin further before radiative cooling can proceed at the normal rapid rate. The ground temperature and air temperature can differ significantly on Mars due to the low density of the atmosphere. On Earth, the atmosphere is thick enough that air and ground temperatures generally track each other closely. On Mars, the thin air exchanges heat poorly with the surface. It's possible to have soil temperatures well above freezing, while the air a meter above the ground remains below zero. One calculation suggested that if you stood on the equator at noon during summer, it might feel like spring at your feet where the warm ground radiates heat upward, but like winter at your head where the air remains cold. The temperature gradient with height can reach 15 to 20 degrees Celsius over just a few meters. The Perseverance rover, currently operating in Jezero crater, continues to provide temperature measurements that add to our understanding of Martian climate. Recent data showed ground temperatures ranging from approximately -93 degrees Celsius to +17 degrees Celsius, while air temperatures near the surface range from about -83 degrees Celsius to -13 degrees Celsius. These measurements, taken at a location around 18 degrees north latitude, demonstrate the typical diurnal cycle and the difference between surface and air temperatures. Frost forms regularly on the Martian surface during cold nights, particularly at higher latitudes. Water vapor in the atmosphere, though scarce, can condense as ice when temperatures drop below the frost point. In the morning, as the sun rises and temperatures increase, this frost sublimes back into the atmosphere. The process creates a daily cycle of deposition and sublimation visible in images from landers and rovers. Carbon dioxide frost can also form during the coldest parts of winter at mid to high latitudes, creating bright patches that persist for weeks before temperatures rise enough to cause sublimation. The temperature conditions on Mars create an environment where liquid water cannot exist in stable form at the surface. Even if ice were heated above 0 degrees Celsius, the low atmospheric pressure would cause it to sublime directly to vapor rather than melt. The combination of cold temperatures and low pressure places the surface conditions of Mars almost entirely outside the range where liquid water is stable. There may be brief exceptions at the warmest times and lowest elevations where both temperature and pressure reach values that could theoretically allow liquid water, but any such occurrence would be fleeting. These temperature extremes affect every process on Mars. Rock weathering proceeds through temperature cycling that causes expansion and contraction, gradually breaking down surface materials. Ice deposits sublimate or remain frozen depending on local conditions. Atmospheric circulation is driven by temperature differences between the equator and poles, between day and night. The formation and dissipation of clouds depends on temperature variations that control when water vapor condenses or sublimes. Every aspect of the Martian environment connects to temperature in some way. The planet cycles through its temperature patterns with absolute regularity. The same daily and seasonal variations repeating year after year. The temperatures rise and fall as Mars rotates and orbits, warming and cooling in response to the changing angle and intensity of sunlight. The patterns will continue as long as Mars maintains its current orbital configuration and atmospheric pressure, though over millions of years, variations in orbital parameters will cause slow changes in the climate system. For now, the temperature regime remains stable, cold but predictable, harsh but consistent, creating an environment defined by extremes that occur every day and every year without fail. While Mars today is cold and dry, with temperatures and pressures that prevent liquid water from existing on the surface, the planet retains abundant evidence of a wetter past. Valley networks, outflow channels, lake beds, and minerals that form only in the presence of water tell the story of ancient rivers, lakes, and possibly oceans that existed billions of years ago. This evidence does not indicate that Mars is currently undergoing active water erosion, only that water played a major role in shaping the planet's surface early in its history. The valley networks on Mars resemble river drainage systems on Earth. They branch and merge in patterns consistent with water flow, collecting in tributaries and flowing downhill toward larger channels. These networks appear primarily on the ancient cratered highlands of the southern hemisphere, carved into terrain that dates back more than 3.5 billion years to a period called the Noachian era. The valleys are typically several kilometers wide and hundreds of meters deep, though erosion and later deposition have partially filled many of them. The formation of these valley networks required sustained flow of liquid water, which in turn required climatic conditions quite different from today. Temperatures would need to have been warm enough, at least occasionally, to allow liquid water to exist on the surface. Atmospheric pressure would need to have been higher to prevent rapid evaporation or sublimation. Some researchers propose that early Mars had a thicker carbon dioxide atmosphere that created greenhouse warming sufficient to raise temperatures above freezing. Others suggest that warming events might have been temporary, triggered by volcanic eruptions or asteroid impacts that injected heat and gases into the atmosphere. Outflow channels represent a different class of water-carved features. These are enormous channels, sometimes hundreds of kilometers wide, that emerge fully formed from chaotic terrain and extend for thousands of kilometers across the surface. Unlike valley networks, which show branching tributary patterns suggesting gradual erosion, outflow channels appear to have formed catastrophically through sudden releases of enormous quantities of water. The channels have streamlined islands, scoured bedrock, and other features consistent with flooding on a massive scale. The source of water for these catastrophic floods appears to have been subsurface reservoirs. Mars likely contained significant quantities of groundwater early in its history, held in porous rock or as ice mixed with regolith. If this water was suddenly released, perhaps through volcanic heating or pressure buildup, it could have erupted to the surface and flowed across the landscape in floods that dwarfed anything experienced on Earth. The water would have flowed rapidly downhill, carving the outflow channels before freezing, evaporating, or seeping back into the ground. Many outflow channels terminate in the northern lowlands, the vast plains that cover much of the northern hemisphere at low elevations. Some researchers have proposed that water from the outflow channels and other sources may have accumulated in this region, forming a northern ocean early in Martian history. Evidence for this ocean includes features that resemble ancient shorelines at consistent elevations, though the interpretation of these features remains contested. An ocean would have required a substantially different climate than exists today, with enough atmospheric pressure and warmth to maintain liquid water on the surface for extended periods. The presence of specific minerals on Mars provides strong evidence for past water. NASA's Opportunity rover discovered hematite in Meridiani Planum, an iron oxide mineral that often forms in the presence of water. The rover later found jarosite, a sulfate mineral that forms in acidic water. NASA's Spirit rover identified goethite, another iron oxide that forms in wet conditions. The Curiosity rover, exploring Gale Crater, has found extensive clay deposits that form when water interacts with volcanic rock over long periods, altering the minerals into hydrated silicates. These minerals tell a story of different aqueous environments that existed at different times in Martian history. Some minerals formed in pH-neutral water, suggesting lakes or groundwater that might have been hospitable to life as we understand it. Other minerals formed in acidic or briny conditions that would have been more challenging for life, but still involve liquid water. The variety of water-related minerals found at different locations indicates that multiple episodes of water activity occurred, possibly spanning hundreds of millions of years. Gale Crater, where the Curiosity rover operates, shows particularly clear evidence of past water. The rover has climbed through layers of sedimentary rock that appear to have been deposited in a lake that existed within the crater billions of years ago. The layers show variations in grain size and composition consistent with deposition in standing water, with finer materials settling in quiet water and coarser materials deposited during higher energy events. The presence of these lake deposits suggests that Gale Crater contained water for at least millions of years, perhaps intermittently over a longer period. Jezero Crater, the landing site for the Perseverance rover, was selected specifically because orbital observations indicated it once contained a lake with inlet and outlet channels. The rover is currently exploring what appears to be an ancient river delta where a channel entered the lake, depositing sediments in a fan-shaped structure. The delta contains layered rocks consistent with deposition by flowing water, and the rover has collected samples from these layers for eventual return to Earth. Analysis of these samples may provide detailed information about the conditions in the ancient lake and whether it could have supported microbial life. The evidence for past water on Mars does not necessarily indicate continuous oceans or rivers. The water may have been present only episodically, appearing during brief, warm periods separated by long intervals when the surface remained frozen and dry. Volcanic eruptions could have released water and greenhouse gases into the atmosphere, temporarily raising temperatures and allowing liquid water to flow. Asteroid impacts could have melted large volumes of ice, creating temporary lakes that froze again, as conditions returned to the cold baseline. The geological record preserves evidence of these events without revealing how long they lasted. The loss of water from Mars's surface appears to have occurred gradually over hundreds of millions to billions of years. As the planet lost its magnetic field, solar wind began stripping the atmosphere away. As atmospheric pressure dropped, liquid water became unstable and evaporated or sublimed. Much of the water may have escaped to space, broken down into hydrogen and oxygen by ultraviolet radiation in the upper atmosphere, with the hydrogen escaping while the oxygen reacted with surface rocks. Some water likely retreated underground, freezing into permafrost where it remains today. Current Mars retains significant quantities of water in the form of ice at the poles, in permafrost at mid and high latitudes, and possibly as deeper groundwater. Estimates suggest that if all this ice were melted and distributed across the surface, it would create a global ocean tens of meters deep. But this water is locked away in solid form, stable only because it remains cold and protected from the thin atmosphere. On the surface, in the present climate, water cannot exist in liquid form except perhaps fleetingly under the most favorable conditions. The contrast between ancient Mars, with its flowing water and lakes, and modern Mars, cold and dry, represents one of the major transitions in the planet's history. Understanding this transition requires understanding what changed in the Martian climate system and why those changes occurred when they did. The loss of the magnetic field appears to have been crucial, allowing atmospheric escape to proceed more rapidly than it could have if the field had persisted. The cooling of the interior, shutting down volcanism that had replenished atmospheric gases, also played a role. What remains is a planet that bears the marks of its wetter past, but exists in a state that cannot reproduce those conditions. The channels lie empty, carved into ancient terrain. The lake beds are dry, filled with sediment and dust. The minerals that formed in water remain stable in the cold, dry environment, preserving evidence of the water that created them billions of years ago. Mars holds this evidence like a memory, a record of a time when its surface was more dynamic, more active, more similar perhaps to early Earth. The sun sets on Mars much as it sets on Earth, sinking below the western horizon as the planet rotates. But the Martian sunset differs in character from the sunsets we experience on our world. The sun itself appears smaller, only about 2/3 the diameter it shows from Earth, a consequence of Mars's greater distance from our star. The colors of the sky shift differently due to the composition and pressure of the atmosphere and the dust suspended within it. During the day, the Martian sky appears butterscotch or pinkish tan, colors created by the scattering of sunlight, by fine dust particles suspended in the atmosphere. The dust particles, averaging about 1.5 micrometers in diameter, scatter light differently than the nitrogen and oxygen molecules that dominate Earth's atmosphere. Where our sky appears blue because shorter blue wavelengths scatter more effectively than longer red wavelengths, the Martian sky takes on warmer hues because the larger dust particles scatter all wavelengths more uniformly, with a slight preference for the longer red and yellow wavelengths. As sunset approaches and the sun descends toward the horizon, the colors of the Martian sky begin to change. Light from the low sun must pass through more atmosphere to reach an observer, and the dust in this longer path scatters light more completely. The area around the sun takes on a bluish tinge, appearing almost the opposite of the sunset colors on Earth, where the sky near the sun glows red and orange. This blue glow results from the same dust that makes the daytime sky appear tan. When sunlight passes through dust at a low angle, the forward scattered light, the light that continues roughly in its original direction, preferentially includes shorter wavelengths, creating the blue glow around the setting sun. Away from the sun, toward the opposite horizon, the sky retains its warm colors and may even appear more intensely orange or red as the sun drops lower. The contrast between the blue glow near the sun and the reddish sky elsewhere creates a color pattern unfamiliar to observers from Earth. Spacecraft on Mars have captured images of these sunsets, showing the distinctive blue halo surrounding the sun against a brownish-red sky. The images reveal a delicate beauty in the Martian twilight, though the colors appear muted compared to the vivid sunsets on Earth. After the sun disappears below the horizon, twilight continues for a period determined by the depth of the atmosphere and the scattering properties of the dust. On Earth, twilight can last for an hour or more after sunset, as light scattered by the upper atmosphere continues to illuminate the surface. On Mars, with its thinner atmosphere, twilight is briefer, fading more quickly into darkness. However, if the atmosphere contains significant dust, twilight can last longer as the dust particles continue to scatter sunlight even after the sun has set. The stars emerge as the sky darkens, appearing one by one as the scattered sunlight fades and allows their faint light to become visible. From Mars, the stars would appear much as they do from Earth, though the constellations would show subtle differences due to the change in viewpoint. The two planets are close enough in the solar system that the patterns of stars remain largely recognizable, but bright stars might appear in slightly different positions relative to one another. The overall appearance of the night sky from Mars would be familiar to anyone who has studied the stars from Earth. Earth itself would be visible from Mars, appearing as a bright blue-green star near the sun. At maximum separation, Earth would lie about 47 degrees from the sun in the Martian sky, visible in the evening after sunset or in the morning before sunrise. The moon would appear next to Earth, close enough that the two might be difficult to distinguish without optical aid, though Earth would shine more brightly. Together, the Earth-Moon system would be one of the brightest objects in the Martian sky apart from the sun, readily visible to any observer who knew where to look. Venus would also be visible from Mars, appearing as it does from Earth as a brilliant evening or morning star. Mercury would be more difficult to see, remaining close to the sun and visible only during brief windows after sunset or before sunrise when atmospheric conditions were favorable. Jupiter and Saturn would appear much as they do from Earth, bright wandering stars moving slowly against the background constellations. The outer planets Uranus and Neptune would require optical aid to see, just as they do from Earth. Mars has no large moon to illuminate the night sky. Phobos, despite being the larger of the two moons, appears only about one-third the size of Earth's moon, as seen from the Martian surface, and it reflects less light due to its dark surface composition. From most locations on Mars, Phobos would be visible crossing the sky several times each night, rising in the west and setting in the east due to its rapid orbital period. It would appear as an irregularly shaped object rather than a circular disk, with its potato-like form evident even to the naked eye when it was overhead. Deimos would appear even smaller, more like a bright star than a disk, contributing little light to the nighttime landscape. Without a large moon to create moonlight, Martian nights would be darker than nights on Earth when the moon is up. Starlight and the faint glow from Phobos and Deimos would provide the only natural illumination. In areas covered by light-colored dust, this starlight might reflect enough to allow some visibility, but in regions with darker soil or rocks, the darkness would be nearly complete. The lack of atmospheric glow, which on Earth sometimes creates a faint background light even on moonless nights, would make the Martian night sky exceptionally dark, away from any artificial light sources. Meteors would occasionally streak across the Martian sky as particles from space entered the atmosphere and burned up from friction. The thin Martian atmosphere would cause these meteors to appear different from those seen on Earth, burning at higher altitudes where the atmospheric density is sufficient to cause heating, but lower than the altitudes where meteors typically burn up in Earth's thicker atmosphere. The frequency of meteors might be similar to Earth, as both planets orbit through similar regions of interplanetary space and encounter similar populations of meteoroids. The night would pass in stillness, broken occasionally by wind, the only sound in an environment without liquid water to flow, without rain to fall, without life to call or rustle through vegetation. As dawn approached, the eastern sky would begin to brighten, first with a subtle glow, then with increasing light as the sun prepared to rise again. The stars would fade one by one, disappearing into the growing daylight. Phobos might still be visible, a dark shape crossing the brightening sky, or it might have already set in the east, completing another of its rapid orbits. As the sun rose above the eastern horizon, the cycle would begin again. The sky would transition from the twilight colors to the daytime butterscotch. The temperature would begin to climb from its nighttime low, and another sol would commence on Mars. The pattern repeats with the precision of orbital mechanics and planetary rotation, each day following the same sequence, each sunset and sunrise echoing the ones before and previewing the ones to come. The twilight periods, those transitions between day and night, represent moments of particular beauty on Mars, when the colors of the sky shift and change, when the temperature moderates briefly between the extremes of day and night, when the quality of light creates conditions unlike any other time in the Martian day. These periods last only minutes to perhaps an hour, brief intervals in the 24-hour and 40-minute Martian day, but they create a rhythm to the passage of time, marking the boundaries between light and dark, warm and cold, visible and invisible. We have traveled across Mars together, moving through its atmosphere and across its surface, examining its volcanoes and canyons, its ice caps and dust storms, its two small moons, and its temperature extremes. We have looked at evidence of ancient water and considered the twilight that marks each Martian day. Throughout this journey, we have encountered a world both similar to and different from Earth. A planet that follows the same physical laws but produces different outcomes due to its particular circumstances. Mars continues to turn in the darkness, carrying its burden of rust-colored dust, its ancient volcanoes, its frozen caps. The planet existed before we knew of it and will continue to exist after all human memory has faded. It maintains its orbit around the Sun with the same constancy it has shown for billions of years. The dust storms will rise and fall. The ice will freeze and sublime with the seasons. Phobos will continue its spiral inward toward eventual destruction. The surface will slowly change through wind and dust transport while remaining fundamentally the same. What we know about Mars comes from careful observation and measurement, from spacecraft that have orbited the planet and rovers that have touched its surface. Each mission adds to our understanding, filling in details and sometimes revealing new mysteries. The picture we have is incomplete but grows more detailed with each new dataset, each new image, each new measurement. What appears in this account represents our current understanding, subject to revision as new information becomes available. If you have found value in this exploration, if these facts about Mars have provided you with a moment of contemplation or helped you rest, I invite you to like this video and subscribe to the Nebula Nights channel. Subscribing allows you to continue this type of quiet exploration, encountering other topics presented in the same calm, detailed manner. Each subscription supports the creation of more content like this, more opportunities to learn about the universe while letting your mind settle into a state of peaceful attention or drift towards sleep. There is more to discover about Mars and about countless other topics in astronomy and planetary science. The universe contains phenomena at every scale, from the quantum processes that govern matter to the vast structures of galaxies and clusters. Each topic offers opportunities for contemplation, for learning, for the quiet satisfaction that comes from understanding how things work. Nebula Nights will continue to explore these topics, presenting information in a way that values accuracy, thoroughness, and a tone that respects the need for calm in an often chaotic world. Thank you for spending this time exploring Mars. Whether you listened while resting, while falling asleep, or while simply taking a break from the demands of daily life, I hope this journey across the red planet has provided something of value. The facts presented here will remain true regardless of whether anyone remembers them. Mars will continue its orbit, and these processes will continue their slow unfolding across geological time. The universe is vast beyond comprehension, filled with worlds and phenomena that exist whether we observe them or not. Mars is just one planet among countless objects in space, yet it holds enough complexity and history to occupy our attention for hours. This is the nature of reality at every scale. Even the smallest subjects contain depths that reward careful examination. Even the most distant objects connect to us through the physical laws that govern all matter and energy. If you found this exploration worthwhile, please consider liking this video and subscribing to Nebula Nights. Your support helps create more content like this, more opportunities to explore topics in depth while maintaining the calm, measured approach that makes these videos suitable for rest and relaxation. There are many more subjects to examine, many more facts to discover, many more quiet journeys to take through the knowledge we have gathered about the cosmos. Until next time, rest well. The stars will continue to shine, the planets will continue their orbits, and Mars will continue turning in the darkness, patient and persistent, as it has done for billions of years and will do for billions more.